Hello, this is Dr. Muhammad, and this is another video under Engineering Mathematics course, still under the matrices topic. Today I'm going to talk about non-homogeneous system. Okay, so let's have an introduction and understand some issues related to non-homogeneous system before going into the details. So first of all, we want to recall what is the meaning of non-homogeneous system as we have explained it before. So whenever that you have a set of equations, as you can see here, which is, as you can see, it has coefficient multiplied by one unknown, which is x1, and then in the same equation we'll have different coefficients multiplied by m unknowns. So in every equation we have m unknowns, and in the right hand side of the equation we are going to find that there is a value which is b1. If we have different set of equations, we're going to have on the right hand side a vector which is going to be the vector of b. We're going to call it b, okay, and this b is going to be the right hand side of the matrix form if we want to represent this linear system of n equations in m unknowns. We're going to put it in a matrix form like this, which is A times x equal to b. I think that we are familiar with this. Where this A, as we said many times, it is the coefficient matrix. Which is including A11, A21, A31, A41 until AN1 in the first column, and similar for the next columns until that we reach the last column, which is the last or the M unknown. Okay. In the right hand side, the system is going to be called non-homogeneous if the right hand side has at least one value to be not equal to 0. So for example, if b1 and b2 and b3 and all of them they are zeros, as you can see, and only one of these entries are having a value which is 2, for example, larger than 0 or different than 0, in this case we are going to tell that this system is non-homogeneous. However, if this vector, which is vector b, the right hand side values, if all of them they are zeros, in this case we are dealing with homogeneous system. Okay, it is homogeneous system. So in our case today we are going to talk about the non-homogeneous system. So at least the right hand side, one of the entries should equal to a number that is not equal to 0. Okay. In this matrix form x, it is the vector of the unknowns. We start with x1 and end with xm. As you can see, in each equation we have x1 and end with xm. And the matrix B, which is the right hand side, okay, it is going to be b1, b2 until bn. So we have m unknowns and we have n equations. Okay, m unknowns and n equations. Okay, now let's go to the next to understand more about this. The system is non-homogeneous if at least bj does not equal to 0. bj, as I said, any entry of the right hand side. Non-homogeneous systems differ from linear systems in two significant ways. If we are going to say what is the main difference between homogeneous and non-homogeneous system, then we are going to address two main issues that need to be understood, or two main differences. The first one is a non-homogeneous system may have no solution. Okay, that's very important. In the non-homogeneous system, okay, or a non-homogeneous system may have no solution. What is the meaning of no solution? Let's have this example to understand. If we have a set of two equations in two unknowns, 2x1 minus 3x2 equals 6, and 4x1 minus 6x2 equal 8. This is our system. If you look to the first equation and look to the second equation, you are going to find that if we multiply the first equation by 2, it will be 4x1, which is the first term here, and 6x2, which is the second term here, and in the right hand side it should be 12, right? But actually it's not 12, it is 8 here. Okay, so this system can have no solution. As we said, there is no solution for this system, as you can see. Okay, that's the meaning of the word no here. If 2x1 minus 3x2 equals 6, then 4x1 minus 6x2, which is the second equation here, the left hand side of it, must equal to 12, not 8. Okay, here it is 8. Okay, you understand? So this means that this system has no solution. So this is considered to be the first difference between the non-homogeneous and the homogeneous systems. Now, okay, we call AX equal B. Okay, we are going to give it a name. We're going to call it consistent if there is a solution. But if there is no solution, the system is inconsistent. So for the system, the non-homogeneous, we are going to call it either consistent system, okay, or we are going to call it inconsistent. Okay, or inconsistent. This is only a kind of abbreviation. Consistent or inconsistent. If it has no solution, then it is inconsistent, as we said here. But if it has a solution, then it is going to be consistent. Okay. And the second difference is a linear combination of solutions of a non-homogeneous system, AX equal B, need not be a solution. In the homogeneous system, if you remember, we said that we can add up the two solutions so that we can get another solution, a third solution. Okay, but actually this doesn't apply in the non-homogeneous system. In the non-homogeneous system, a linear combination of solutions of a non-homogeneous system, which is AX equal to B, need not be a solution. It's not. Need not to be like this. It is maybe if we are going to talk about if there is a solution or not based on the linear combination of the solutions of the non-homogeneous system, the answer is no, need not to be a solution. Therefore, the solutions do not have the vector space structure seen in the homogeneous case. If you go back to the case of the homogeneous system, you are going to understand this. So linear combination for non-homogeneous system is not a solution. These are considered the most two important differences that you can see for the homogeneous versus non-homogeneous system. Okay, two main equations, or two main differences. Okay, now let's go to the second part, which is related to the solutions also of the non-homogeneous system. Okay. Nevertheless, solutions of AX equal B, which is the non-homogeneous system, do have a property that parallels that for solutions of the linear second order differential equations. We will call AX equal to 0 associated homogeneous system. So as you know that we have A times X equal to B, this is considered to be NH, which is non-homogeneous system. Okay, we are going to find now okay, that there is a system called associated homogeneous equation, where that the left hand side is the same as the non-homogeneous system, but the right hand side is going to be zeros, a vector of zeros. This we call it H, homogeneous. Okay, homogeneous system. This we call it homogeneous system. Okay, so we are going to claim that the difference of any two solutions of non-homogeneous system is a solution not for this system, but for the associated homogeneous system. So what is the meaning of this? Let's assume that we have a first set of solution of homogeneous system. Let's assume that we have ax equal b. This is the system. We will replace this x with the solution. We call this solution u1, which is u1 here. So a u1 equal to b. And we are going to claim that there is another solution for this non-homogeneous system, which is going to be u2. So if we say that we have u1 and we have u2, then we are going to put this substituted back in the original equation, and we are going to look to it again. So we have au1 equal to b, au2 equal to b. Then subtract both from one another. So we're going to have a times u1 minus u2 equals to a u1 minus a u2 equal to, the right hand side is going to be b minus b, right? 0 minus 0. So it is going to be, b minus b, which is going to give us 0 at the end. Okay, the vector of 0. Okay. In this case, now we are having a times what? u1 minus u1 equal to 0, right? This is what? u1 minus u1? It is, exactly, it is homogeneous equation. A times something equal to 0. So this means that u1 and u2 of the non-homogeneous equation, the difference between them, which is u1 minus u2, is considered to be exactly a solution for the associated homogeneous equation. Okay, so this is what we are claiming in this. Okay, so this explanation would help you in understanding the coming parts of the relation between homogeneous and non-homogeneous equations. Okay, now let's go to the next part and put some theorems before going into the examples. Let's talk about this theorem. Let H be the general solution of the associated homogeneous system. Okay, associated homogeneous system. So we have like AX equal to 0, vector of 0. It has a H, which is what? It is a solution for the associated homogeneous equation. And let UP any particular solution of AX equal B. And we have the non-homogeneous system, which is AX equal to B. Its solution, particular solution, is going to be UP. Okay, let's assume that we have UP for this non-homogeneous system. Then the expression H plus UB, the expression H plus UP, contains every solution of the non-homogeneous system AX equal to B. Right? And this is very common and very similar to what we have explained before when we were talking about the set of differential equations, if you remember. So in general, if you have a non-homogeneous equation AX equal to B, its particular solution is going to be UP. And if the associated homogeneous equation, which is AX equal to 0, you've got a solution for it, general solution for it, which is H, then the H plus UP is considered to be a general solution. It contains this solution, contains every solution of the non-homogeneous AX equal to B. Okay? Take care, we have different types for the non-homogeneous system. Different types, I mean, of solutions. We have particular solution, which means that it is depending on some, or it's only one solution for a specific case. We call it U particular. But actually this is not a general solution. It is particular solution, specific solution, if you want to call it. But we want, whenever we solve the non-homogeneous system, we need a general solution, a type of a solution that contains every solution possible for the non-homogeneous system. This one, which is H plus UP, is containing, or it contains every possible solution for the non-homogeneous system. Okay? Okay. A kind of corollary of this theorem, a consistent non-homogeneous system AX equal B has a unique solution. Okay? When we can obtain this unique solution, if and only if the associated homogeneous system has only the trivial solution. Well, that's very nice, because I think that you have asked yourself now how we can obtain UP, which is the particular solution. The answer is we should look to the associated homogeneous equation. If it has trivial solution, and we know well how to check for the homogeneous system if it has trivial solution or not from the previous video. In this case, AX equal B is going to have unique solution. Okay, so that's the case. So if we have AX equal to 0, vector of 0, which is the homogeneous, associated homogeneous equation, if it has trivial solution, then this means that the AX equal to be the non-homogeneous system is going to have what we call it unique solution. Unique solution, okay? Unique solution. Unique solution means what? Means that there is only one solution for the system. There is no general solution like this. It is only unique solution. Okay? So a consistent homogeneous system AX equal B has a unique solution if and only if the associated homogeneous system has only the trivial solution. Okay? Have only the trivial solution. Okay. Okay, now let's go to some examples. So now it is only a kind of comment on the textbook regarding this theorem. The corollary follows from the fact that the non-homogeneous system has a unique solution exactly when H is 0. That's right. Whenever this H is going to be 0, this means that our solution is going to be UP only, which is unique solution in this case. But if UP plus H, which does not equal to 0, then we have general solution. Okay? So Theorem 713, which is this theorem, suggests a strategy for finding all solution of AX equal B when the system is consistent. Let's see. So we have like 3 different steps in order to get, or the steps for finding the general solutions, the general solution of the non-homogeneous system. We have 3 steps. The first one is find the general solution H of AX equal B, AX equals 0, which is we call this associated homogeneous equation. And step 2, find any one solution which is UP of AX equal B, which is particular solution for the non-homogeneous system, which is our main focus for today's video actually, because step 1 already we have explained it in the previous video. Okay, so we know how to get the general solution of homogeneous systems. So step 1 already known for us. Now we need to obtain the particular solution for the non-homogeneous system. This is what we are going to explain for today. And at the end, the step number 3, we will put the general solution, which is going to be H plus UP. Okay, so these are the 3 steps that you need to go through. Step 1 already done, previous video. Step 2 is going to be done in this video. You are going to know how to obtain the particular solution of the non-homogeneous system. Okay, now let's go to step 2 in particular and see how we can do it. Okay,
In order to find the particular solution yp, proceed as follows. You need to go through three steps in order to get the u particular. Okay, you need to get or to go through 3 steps in order to get u particular. Actually, using an example would make it much easier, but just I'm going into the important parts here of the steps. So we are going to define n times m plus 1 augmented matrix, which is, we're going to put the coefficient matrix, and we're going to put another column which is having the right hand side. Okay, so now we form the augmented matrix by adjoining the column of matrix B as an additional column to the coefficient matrix A. Okay, so now this is the first thing that we're going to do, which is making the augmented matrix. Step number 2, we're going to make reduction for the augmented matrix. This augmented matrix, we're going to make reduction for it. So from augmented matrix, we can reduce it. How to reduce it? Already you are familiar with this now if you already have solved the assignments or the in-class and home assignments. So we're going to find that the reduced matrix, which is A, B, and between parentheses R here means that reduced, it is going to be the right hand side here, which is B. It is going to be another vector, which is C. However, A is going to be A reduced, right? So that's the case. Whenever that we are having A, B here, okay, reduced, this means that we are going to have, after reduction, we're going to find that A is in the reduced form, and this B is going to be another vector based on our row operations that we have done. It is going to be another vector called C, for example. Okay, that's what we are going to do, in which the first m columns is going to be the reduced matrix AR, and the last column is whatever results from B after the row operation used to reduce or to make the reduction for AR. Okay, so B is going to be C after making the reduction on A to obtain AR. Okay, whatever it will, we will get here. Okay. Okay, solutions of the reduced system AR x equal C are the same as solution of the original system. This is the main idea here. So now this system, which is ARX equal to C, ARX equal to C, this is the same solution as the original system, which is AX equal B. Then this is non-homogeneous system and this is non-homogeneous system. Well, so we didn't solve anything here. If we are going to have another non-homogeneous system to solve, then it is going to complicate the issue. But actually no, it will not complicate, because there is simple thing here. It is AR. Here we have the reduced matrix, right? This will greatly simplify the solution. Greatly simplify the solution. You're not going to find that you are spending any time for getting the solution of this system. Okay, so now it adds up to, or on top of what we have mentioned before regarding the importance of reduction or the reduced echelon form, it helps us in solving the systems. It helps us a lot in solving the systems. Okay, you are going to understand this very well in the next example. Okay, and now the step number 3, from ARC, read a particular solution, which is UP, as we're going to see now, when added to the general solution H. Okay, so now if you have UP plus H of the associated homogeneous system, we have the general solution of AX equal to B. Okay, so we are going to look to some examples and you are going to understand what we have said now. Okay, let's go to this example. We want to solve this system, which is, this is the coefficient matrix. This is X, which is we have X1, 2, 3. It's a vector. And we have the coefficient matrix, as you can see, equals to the right hand side is 8, 1 and minus 2.
8, 1, and minus 2. The first step is to reduce the augmented matrix. So we are going to form the augmented matrix. This is the augmented matrix now. We will put the coefficient matrix as it is, and we are going to add a column here, which is the right hand side, 8, 1, and minus 2. After that, we are going to carry out the reduction procedure on the 3 by 4. This is a 3 by 4 augmented matrix. We're going to reduce it. We're going to make leading entry at each row. So after making the reduction, please do it by yourself and check the results. Then you're going to find that the reduced matrix for this system is going to be, as you can see here, 1, 1, 1 on the diagonal. This is the reduced matrix, take care. So we have reduced the system now. And when you look to this 3 by 3 matrix is what? It is the reduced matrix, right? AR. And this column is whatever results from this column after the row operations. After row operations, we do not know what will happen for this column, but it gives us this value, this column here, this vector, which is C. But we found that AR, fortunately, it is I3. It is the identity matrix, right? This means what? Exactly. C is whatever results, as we said, C is whatever results in the fourth column when reduce A. The first 3 columns, okay, of this augmented matrix is going to be the reduced matrix, as we said. Okay, now this is, can you remember something we told before regarding whenever that you reduce a matrix and you find that the reduction is going to be the identity matrix? Yes, we are going to see this. This reduced augmented matrix represents the reduced system I3 X equals C, which is the system. This is very easy to read now because we have X here, right? I3 means that we're going to read from each row, we're going to read only one unknown. Okay, so directly we can read from the previous here. The first row here means what? Means that x1 plus 0x2 plus 0x3 equals to 0. So this means that x1 equal to 0. And here, similar, we're going to find that this means that x2. So 0x1 plus 1x2 plus 0x3 equals to 5 over 2. Right? This means that x2, let's see here, x over 2 going to be 5 over 2. And x3, let's go back, this is x3 would equal to 3 over 2, right? And x3 equal to 3 over 2. What is this? It is the solution. Is it difficult or easy? It is very easy actually to read it. This is the advantage of having our system to be reduced. That we're not going to solve anything. We can read the solution directly. After making the reduction, we can read the solution of the system directly from the reduced form. Okay, so now we have read it and we have obtained x1, x2, and x3. Okay, from this we directly read a solution of the reduced non-homogeneous system. In this example, this solution is unique. Okay, this is unique. Why it is unique? Because do you remember when we said that the general solution is going to be H plus UP? Here, H is what? The solution of the associated homogeneous equation. What is the associated homogeneous equation? AX equal to 0. But when we reduce this A, when we reduce it, we found that it equals to I3 times X equal to 0. This means what? Go back to the previous video and you are going to find that when we have the reduced matrix, this is AR, whenever we have the reduced matrix to be the identity matrix, this means that the homogeneous system is going to have trivial solution. Trivial solution means that it is going to have zeros. All the unknowns is going to have zeros, right? So when we add this trivial solution, which we call it H, to the UP, then we are going to have U, which is unique. We call it only, we are going to have UP here, which is, this is 0, going to be 0 here. So in this case, we are going to have unique solution, which is particular solution only. Okay, so the reason for that this non-homogeneous system has a unique solution is that the associated homogeneous equation, which is AX equal to 0, its general solution equal to trivial solution, which is 0, trivial or equal to trivial solution. Okay, so this means that we are going to have a unique solution. Unique solution means that the non-homogeneous system will not work unless that it equals to this very unique solution. Other values it is not allowed. So consistent with treating the system as a matrix equation, we usually write the solution in terms of column matrices in this example. Okay, so we're going to put, so x1 equal to 0, x2 must equal to 5 over 2, x3 equal to 3 over 2. So it has a unique solution. Okay, so now so I hope that you have understood this example, because it is really important for us to understand how the reduced form is making our life easier whenever that we deal with the non-homogeneous system. Okay. Now let's go to the next another type of example that we have here. And this example, we have seen that this system, do you remember the system that we said that it has no solution? Okay, we're going to explain now why it does not have a solution, okay, by making our 3 steps that we have explained before, and you're going to understand why it does not have a solution. So already we said about this. We will see how this conclusion reveals itself when we work with the augmented matrix, that it has no solution here. Okay, so it has no solution. Now let's deal with it as usual based on our steps. So we will put the coefficient matrix. We have 2 and 4. We have -3 and -6. So we have -3 and -6. And we have 6 and 8, which is 6 and 8 here. Then we are going to reduce this form. So reduce it using our row operations. Then we are going to find that the reduced matrix is going to consist of AR and another vector here, the 4th or the 3rd column here. So AR, if you read it, it is going to be, as you can see here, we have one row which is non-zero row, and we have another row which is 0. So AR here, AR equal to 1 and 0, -3 over 2 and 0. So we have here AR and we have these values here. So how many non-zero rows here? 1 only. The rank of AR is 1, because non-zero rows is, the number of non-zero rows is 1. Okay. But the augmented matrix, if you look to the augmented matrix, you are going to find that how many non-zeros? The augmented matrix is 2 by 3, right? But AR, which is this one, it is 2 by 2, right? So how many non-zeros for the augmented matrix? 2. We have, this is the first row, this is the second row. The second row, it has -4, so this means that it is non-zero row, even that it has 2 zeros here, but not all of them are zeros. It is -4 is non-zero. So we have the rank, okay? So the rank of the augmented matrix, okay? The rank of augmented matrix is going to be 2. However, the rank of A, of the coefficient matrix, the rank of it is 1. Okay, so we have different ranks here.
keep these ranks into your mind now. I'm going to recall, or I'm going to revisit it again. Okay, now let's go. Shift E, I want only to remove this. Now, let's read here the solution. Look here. Read this equation, which is the second equation of the augmented matrix. It tells us 0x1 plus 0x2 equals to minus 4, right? Can you imagine this? That is 0x1 plus 0x2 equal minus 4? It doesn't work, right? There is something wrong. And this is why we said that this system does not have a solution. Why? Because the equation does not give any logic here. The equation does not give any logic, which can have no solution. Okay, now let's go. We want to form this, okay, into an equation. If you remember when I was talking about the ranking, okay, so the rank of A, rank of the matrix A equal to 1 from the reduced form, and the rank of the augmented matrix, okay, so which is A, B here, this is the augmented matrix, okay, the rank of the augmented matrix is 2 because the reduced form of it has 2 non-zeros. Whenever the rank of the augmented matrix is, or the rank of A is less than the rank of the augmented matrix, as you can see, this is 1 and this is 2, this means that the system does not have solution. Okay, the system does not have solution. That's the importance of knowing the rank of the matrix. This is the importance of knowing the rank of the matrix. Why this happen? Because whenever that we have in the augmented matrix 2 non-zeros, which is the rank of it, 2 non-zero rows, okay, and in the A matrix we have, or the reduced matrix of A, we have only 1 non-zero row, this would always give us such kind of equation, which means that all the coefficients that is multiplied by the unknowns are going to be 0. However, that the right hand side is going to be numeric or value, which does not apply, which is going to give us something like this: 0x1 plus 0x2 equal to minus 4. Okay, understand it now? So that's the meaning here of what we are talking about. Okay, so the ranking now, so now this adds up to something that is very important, which is the importance of ranking. So if you are going to reduce the matrix A, as you obtain it here, and then you are going to reduce the augmented matrix, as we obtain it here also, then the rank of each one would tell us whether that the system has solution or not. So that's the importance of ranking. Okay, that's the importance of ranking. And actually this is what it is being explained here. So we're going to put it in a theorem, okay, which is the non-homogeneous system AX equal to B is consistent. What is the meaning of the word consistent? Exactly, it means that it has a solution. If and only if A, which is the coefficient matrix, and AB, which is the augmented matrix, okay, this is the augmented matrix, okay, and this is the coefficient matrix, okay, have the same rank. So if the rank here is 2 and the rank here is 2, then this system will be consistent, will have solution. But if the rank of the coefficient matrix is 1, for example, and the augmented matrix, its ranking is 2, then the system will not work. This system will be inconsistent, meaning that it does not have any solution. It does not have any solution. Okay? Okay. Now, let's go and see how we can understand it more using equations. We will solve this system. As you can see here, we have a system
which is x1 and x2 and x3, and there is a right hand side here which is b. Then we can form the augmented matrix directly, which is a and b. So we put the coefficient matrix here, 1 minus 4 minus 2. We arrange it based on the coefficient matrix. And the right hand side is, as you can see, 3 minus 5 and 14. 3 minus 5 and 14. So we're going to reduce this augmented matrix. We're going to have the reduction here, make the reduction. So in the reduction, we're going to obtain inside the augmented matrix, A is going by default going to be reduced. So when you reduce it, you're going to find that here it is leading entry 1, another one, and look here, at the end we have what? Yes, zeros for the reduced A. However, the augmented matrix, we found that when we reduce the original augmented matrix, we found that the last column is having 0, 0, 1. This means what? The A, ranking of A is 2. However, the ranking of the augmented matrix is how much? 3. So they are not the same. A R has a kind of less ranking than the augmented matrix, right? So this means what? The system will have no solution. How we can read this? You can read it from the last equation here. Read the last equation. Last equation tells us 0x1 plus 0x2 plus 0x3 equals to what? 1. It does not work. This does not work. This means that this system has no solution. Okay? It has no solution. You understand this? Okay. Okay. Now let's go to another equation or another example and try to understand more regarding it and try to understand more about it. So we are going to solve the system. As you can see, it is a system. It consists of x1, x2, x3 until x6. I think this should be x3. Okay, this is x3. As you can see, on the right hand side, it is, as you can see, minus 3, 1, and 0. And here we put the coefficients of all systems, coefficients of the unknowns. As you can see here, we have arranged the augmented matrix. So this is our augmented matrix, A and B. And we are going to reduce it. So we're going to reduce it. When we reduce, we are going to form AR in the first 6 columns, because we have 6 unknowns. And the last column is going to be the whatever what will be based on the row operations of the last column here. Okay. When we reduce the system or the augmented matrix, we found that we have 1, 1, 1 here. So this means that the ranking of matrix A, this is AR, remember this part is AR. The ranking of AR, okay, rank of A, or it is the number of non-zero rows, or ranking of A or AR, it is going to be number of non-zero rows, it is 3. And the rank of the augmented matrix, okay, which is this B reduced, for example, also it is 3. This means what? Yes, this system, it has solution. It will work for us. Okay, it will work. Okay, because we do not have any equation that is having zeros for all its coefficient of the unknowns. Okay, now let's see how we can work with this. The first 6 columns are AR, and we read from ABR that both A and AB have rank 3. This is what I've explained. So the system is consistent. We call it consistent, means that it has a solution. From the reduced augmented matrix, we see immediately that we are going to arrange it from here. This is the reduced form, so we can read and put the equations in the form. So here, for example, this means that x1
plus 0x2 plus 0x3 plus 27 over 8 times x4. Now, can you look here what is the answer space or the solution space? We have x1, x2, x3, and we have here what? x4, x5, x6, right? This means that it seems that x4, x5, x6 are going to be like the independent parameter, free parameters, okay, free variables, and the other x1, x2, and x3, they are going to be dependent on them, as we have mentioned in the previous videos before, right? So this means that we can end, if we read the equations, these are x1, x2, x3, and you are going in each equation, you're going to find x4, x5, x6, right? Similarly here. Similarly here. This means that x1 and x2 and x3, they are dependent on x3, x5, and x6. So we are going to form it like this. That x1, x2, x3 is going to be as a function of x4, which is going to be, we are going to call it alpha. x5 are going to be, call it gamma, for example. Okay? Or an x6, we're going to call it like, or no need to say this because we're going to put some values for, maybe we're going to put x4, for example, to be, we're going to assume that x4 equal to 8 alpha, for example. So this means that, or we can say that alpha equal to x4 over 8. So this one is going to be alpha, and this we can call it beta. Beta is going to be x5 over 8 also. So beta is going to be x5 over 8, and then gamma, it is going to be, this is gamma, which is x6 over 8. So gamma, it is going to be x6 over 8. Okay, so we have these three constants. Now, if we're going to say them as constant, we're going to arrange it. So we're going to arrange it and put it in this form. That is x, which means that x1, x2, x3, x4, x5, and x6. This is the meaning of the vector of x. And then we're going to put what we have put here. Okay, so the first equation is going to be arranged here, second, third, and then here x4 only, x5, and x6. As we said, it is better to put this in a form that is easy to be understood for us. And this form is going to be that x equal to be alpha times the vector. And this vector, we can read it from here, okay, which is related to alpha, as we said, alpha x4 over 8. And then beta, which is going to be x5 over 8. And then gamma, which is x6 over 8 times these ones. And then plus the last vector here. This last vector is what? It is y particular. So we have like, these are the solution of the system. Okay, this is the solution of the system plus, okay, plus the y particular, plus y particular, which is going to be, or I'm sorry, this is the whole system here, because we have, yes, we have like absolute terms here. We put it here in our equation. So this means that our system is going to have this solution, and this solution is what? It is the general solution. Okay, it is the general solution. Okay, which is H plus UP, as we said, H plus UP, the general solution, with H as the general solution of the associated homogeneous equation, and UP as a particular solution of AX equal to C. Okay. Okay, now let's go to another example and see how we can solve the issue here. We have a system. This is non-homogeneous system, as you can see here. which is 2 minus 5 and 1 and 1 1 1 and so on. So we put the augmented matrix, we put the augmented matrix here, A, and we put the right hand side, which is B, and then we reduce this AB. We're going to have AB reduced. Fortunately, we have that AR, which is this part, it is identity matrix. This means that AR, it is, okay, the reduced matrix of the coefficient matrix is I3. This means what? Yes, that's mean that there is the associated homogeneous equation is having trivial solution, and the non-homogeneous system is going to have what? Exactly, unique solution. Unique solution. So our system, which is going to be the general solution, is going to be H plus U P, right? This is the general solution. H is going to be trivial. Why? Because AR equal to the identity matrix. Then we're going to end up with only one unique solution, which is the particular solution. We can read it easily from the system here. This means that x1 equal to minus 86 over 31, x2 equal to this value, x3 equal to this fraction, okay, which is here, we put it here. So we call this unique solution. We call it unique solution. Okay, so now this is another example for our system, and I hope that you have understood now and mastered everything regarding the non-homogeneous systems using the matrix form. As you can see, we are like having a very important applications of whatever the type of the matrices based on our understanding for the reduction, okay, and the ranking and this kind of stuff. Okay, now I'm going to show the in-class assignment. Okay, so we have this in-class assignment. Find the general solution of the system, or show that the system is inconsistent if it doesn't have a solution, I mean. Write the solution in matrix form. Okay, so we have three systems here. These three systems, you need to solve them based on what we have learned up till now. So as usual in the in-class assignment, you need to stop here, take the system, solve it by yourself, and check the results with the answers that I'm going to show to you. Okay. Okay, now let's go and try to solve the first one together. I hope that you have gone and come back to see the right answer. Now this is our system. Simply we're going to put it in the augmented matrix. As you can see, this is the augmented matrix. Okay, then we're going to have this is the augmented matrix, and putting here this is the coefficient matrix, and this is the right hand side of our equation. So put it here. We're going to reduce. Fortunately, you found that 1 1 1 here in the diagonal. This means that identity matrix for, so AR equals to I3. This means that the associated homogeneous equation does have a trivial solution. Okay, this means that we are going to have a unique solution for this system. So this system will have unique solution. So we're going to read it directly from the reduced form. x1 equal to 1. So because this x means that x1, x2, x2 here, and x3, right? So this means that x1 equal to 1, x2 equal to half, x3 equal to 4. Directly we can read it. Okay, so this is the trivial solution. This is the trivial solution for the associated homogeneous equation, but this is the unique solution for the non-homogeneous system that we have explained. Okay, let's go to the next one. This is our system here. We're going to form our augmented matrix, as you can see it here. Make the reduced form. Found that in the reduced form, when we reduce, it is not the identity matrix, because we have fourth column, it has something here. So this means that we have the rank. What is the ranking of the AR? 1, 2, 3. What is the ranking of the augmented matrix? Also 1, 2, 3. Okay, this means that this system has solution. Okay. Okay, so we are going after reduction. We are going to say, yes, this is what we have found. Rank A equal to rank to the augmented matrix equal 3. So the system has solution. From the reduced augmented matrix, we read the general solution directly. So X equals to, here, this means that X1 here, okay, minus 3 times X4 equal to 8. Okay, so X4, this X4, we are going to put it like alpha, for example. Then we are going to read it like this. X1 equal to 8, and this minus 3 X4, this is here X4, it is going to be on the right hand side with the different sign. So we are going to have 3 here times alpha. That's it. And we are going to repeat for X2 and X3, X2, X3, and then X4, it is going to be 0 here, okay? And then we're going to read alpha times 1 here, okay? Okay, so I think that now you are like familiar with how to do it. And then let's go with the third system, which is, as you can see it here, this is the system which is non-homogeneous system. Put the augmented matrix, it looks like this, reduced form. It seems that the ranking is the same, so we're going to have solution for this system. You can rearrange and you can put the form of the system as we have explained it in the previous videos before. It seems that we have 1, 2, 3, so we have like x1, x2, x3, and then x4 here, x5, and x6. So this means that they are like independent free variables because we have 1, 2, 3 columns. Then we're going to have alpha, beta, gamma, for example. So we have alpha, beta, and gamma, and then we're going to find there is a kind of vector because we have the B reduced here, which is the right hand side always going to be existent for us. Okay, how to do this? You need to go through the previous videos, please, and check how we can obtain the space of the solutions, and we can rank or we can put our solution in a column or in a vector form like this. Okay, now let's go to the final. These are the detailed solution. If you want to go into the details of the solution, it is for you to just to go into the solution. No need to follow exactly what I am saying. You can skip, you can like do other kind of operations. No need, just the final form should be similar at the end. That's it. Okay, so the final form, that's the important. The solution itself and the steps and the whatever I'm doing, it is up to you. You can skip, or you can, if you can do these operations in your mind and you can go through it, it is okay. Okay, and now let's go to the final step for this, which is related to the home assignment. So this is your home assignment. Find the general solution of the system, or show that the system is inconsistent. As we said, write the solution in matrix form. So we have, this is the first system, the second, and the third. You need to work them out. They are pretty similar to what I have explained in the class and pretty similar to the in-class assignment. I think that after being trained with my examples and in class, you will find the home assignment to be very easy for you. Okay, so that's it, and I'm going to share the solution of the home examples or the home assignments, I think, in a separate video during this week, so do not worry about the solutions. Okay, now this is everything about our today's class. I hope you understood well what is the meaning of non-homogeneous system, how we can solve them, what is the main
steps involved and how we can reduce the augmented matrix and read the solution directly from it, and what is the significance of the ranking of the reduced matrix and the augmented matrix. I hope that everything is okay, and I hope the best for you, and see you in the next video. Thank you, and see you soon.